Okay, I think we are live. Let me check. Yeah. Okay, so we are. Okay, so let's start with the second module called state. So I already looked at this state module yesterday night. So what we'll do is we'll go over it quickly and explain everything. What is happening in this module and yeah, so let's start with the state module. So I'll just only looked at this one actually, not the complete module. So I'll start with this one, explain everything, um, maybe a little bit quicker than what I would have done if I was looking at it at the first time, but overall you'll learn whatever is present in that particular module. So let's start with this. Okay. So Flink's managed state is local and fast, durable and scalable. Simple motivation example, you want to do something special the first time, you process an event for each user, then obviously require some state. You could say, okay, I can give that state in local variable if you are dealing with distributed system here, whereas system scale, it becomes increasingly likely that something will happen. But even if you assume your app never fails, what about redeployment? We still need some ways to snapshot and restore data, right? So furthermore, in a cluster, you'll need each node to maintain a key value map of state for the users. Key value map of state for each user that node is responsible for, and have some ways to redistribute the state when scaling the cluster up and down. Okay, so local first is either in memory or the local disk. Durable, you create checkpoints. Vertical scalable is done by RocksDB, and horizontal scalable is done by key space is sharded across the cluster. So let me explain what does it mean, right? So first of all, why do we need state? So um, we need state to do some analytics on the strings or on the data that we are given, right? So for example, in this case, what it's trying to say is we want to store all the users when it's processing for the first time. So how do we know when a user is processed for the first time? We know by storing a particular state whether that particular user is seen before or not, right? So how do we do that? So we maintain a particular state for that particular user if that particular user is already been seen. And if that particular state is not there, that means this is the first time we are processing for that particular user. At that time, we use that state to check whether we have seen it. So that's what it's trying to say, that we need to maintain state. So that's called Flink's managed state. So another thing there are a couple of things that we need to make sure is available for this managed state is local and fast. It has to be local and fast. It cannot, for each messaging, each message, it cannot go and look into some other machine and see what's the state is. For each message, it will add to latency. It will reduce the throughput. Also, it needs, as it's in storage, it needs to be durable. It needs to be durable enough to not it needs to be durable enough to make sure that it doesn't get lost when we are scaling or when we have a fault on the node. So it needs to be durable, and the way it is made durable is by doing checkpointing. The checkpointing is a way to do a snapshot of, in my opinion, snapshot of all the state and store it somewhere in a permanent storage, or make it durable that way. Another thing is scalable, right? So how do we make it scalable? So there are two different ways to make it scalable. One is horizontal scaling, and another one is vertical scaling. So vertical scaling here it looks like it's done by RocksDB, which is used internally, I guess, as a library for Flink. So by vertical scaling, I mean you can add up more RAM, add up more disk, and it should be able to adapt to that particular resource on that particular machine. Other way of scaling is horizontal scaling. So the way horizontal scaling works in general storage as well is we shard the data based on a certain key, right? It could be a simple hash. It could be no, it could be what's that called? Particular hashing technique called I forgot the name. I forgot the name for that hashing technique. What's that called? Okay, let's look at it. Hashing algorithm. Hashing algorithm is no okay. Sharding algorithm. That's consistent hashing. So that's called consistent hashing, which helps you, which minimizes the data transfer across nodes if we are trying to scale up or scale down. So only certain, like for example, if I remember correctly, if we need to scale up and we need to add a particular node, only one node has to transfer the data from it to the new node that we are creating, because the particular range that it used to handle is now been divided into two parts, and that particular range is being assigned to that particular node, a new node, so and taken out from the old node. So this is the basic explanation. There are certain intricacies to it internally, but we'll not go over that. um, yeah, so that is why and we can shard based on particular keys, and keys we need to define the keys, which we'll see later in this particular module. And in this session we'll cover Flink's APIs for working with managed state, keyed state, how to connect streams together and have them share state. So for example, so we have two different streams which are keyed to the same space. For example, one stream has keys A, B, C, three keys, right? Another stream also has keys A, B, and C. So what we can do is, if you want to merge these two streams and maintain a single state for both of these streams, then what we can do is we can just connect these streams together and process these streams together, or maintain a state for each of these keys for both of these streams in a single place. That's what it means when we mention that we can have them share state. Okay, so first thing, okay, so this is what we mentioned by maintaining state for each keys. So okay, so the key is computed for each stream. This key partitions the data that is all element with the key processed by the same operator instance. Certain operators are key aware, process and Windows Flink manages per key state and timers. Okay, so for example, in this case, if we look at this case, what is happening is this um, yellow and pink data is being passed to this particular operator node. and this blue data is being passed to this particular node. That's based on the keys and based on the sharding, right? So a particular key is always passed to a particular operator node. So in this case, blue in this case, and yellow and pink in this case. So this node processes these input, these streams, and produces an output. Every time pink comes, it will be processed by this particular node, and every time a blue comes, it will be processed by this particular node. And so, what we can say is for a particular key, it's processed by the same node, and the state for that particular key is also maintained on the same node. So that's what it means by when it says that Flink manages per key state. It is managing state of each key at a single node, right? And yeah, that's what it means. So let's look at this. All the data of a given key is processed by the same worker instance. The keys are not. So yeah, that the worker instance means the same node operator node. The keys are not attached to the stream records, but rather are computed whenever needed by the. Okay, so the key selector function needs to be fast and deterministic. So okay, so let me explain what it means. So key selector is a class that we write which gives us the key for a particular event, okay, particular message. So what it does is it somehow creates a unique key for a unique message in a deterministic way. So it cannot create different keys for the same message. It needs to create the same key for same message. So it needs to have one-to-one mapping between the message that we have and the key that we are generating out of that message. And the reason, another thing it mentions is key selector needs to be fast. So the reason it needs to be fast is we don't calculate the key every time, or we don't, we don't store the key along with the message. We actually look at the message and create the key out of it. So there is no external, so there is no additional storage which is being used for just for storing key. It's always been created dynamically. It's always been created on spot, let's say. Okay, so key partition state, processing and state are both partitioned by the same key that I already mentioned. All the state is local, which is already mentioned, either on heap of heap in a local local disk packed storage. Okay, so it's either in memory or locally stored on the file system on the particular node. Or it could be in local database as well. That's how it is. So keys works hand in hand with stateful stream processing. For example, consider a case where we want to trigger a special action when we see a new user for the first time. We can only do this if we guarantee that every event for a given user, as I mentioned, will be processed by an operator that will see every event for that. Processed by an operator that will see every event for that user. All the data for a given key is processed by the same node. State is only accessed within the function operator that defines it. Okay. So for each, so I think yeah. So for state, right? So you cannot have the same state for different operator. So for each operator you need to have the same state, in the sense you cannot say that join and select can have the same state because they are different operators in the DAG itself. So they don't have the same state for the same keys Join will have the same state, select will have the same state, but not each other. So that's what it's trying to say. Okay, these keys computed for each string element by key selector. Deterministic keys computed must have valid implementation of hash code and equal. This rules out arrays and LM. Okay, so so we can provide a key selector which calculates a key for each event message, and we need to have hash code function implemented there and equals function implemented there for the comparison between different keys. And the reason we cannot use arrays and enums are they produce non-deterministic keys or hash code for the same key. So it can produce different output, different hashes for the same keys, um, depending on like across different JVMs. So that's what it means. So composite tag can be used as keys. All keys must be, okay, nested field can also be used as keys. So I don't know about nested fields yet, but composite types can be something like keys which is made out of multiple keys, and those multiple keys also needs to have hash code which is deterministic, the same thing that we said about the key. Deterministic, must have hash code and equals as well. Yeah, okay. So let's look at the key are not communicated within the cluster, but as I compare whenever they are needed. As I said already, this is why they must be deterministic, different tasks in different JVMs. Yeah, must compute exactly the same key presented with the same record. That's what I said. Arrays and names don't work as keys because their implementation of hash code are not deterministic across a JVM. That's what I said. Okay, so this has already been done. Okay, so now let's look at some code. So what it's trying to do here is we have certain sensor reading events, and what we are doing is for each of these events we are we have provided a key selector class which has this get key function which actually provides us with the key for a particular reading in the sensor reading. And the what this will do is this will provide us with the sharding based on the key, right? So this particular, so there are 10 different keys which is exist in the sensor reading, and what it can do is it can shard 5 to one node and shard 5 to another node. But this is a stream, this is not processed yet. So it just internally it stores that, and when we process it, it shards at that point of time. So there is another way to simply implement is this, which is looks much easier, but we can do much more complicated stuff here as compared to this. We can call or use certain already existing state in this, or we can call some database API, or we can call some caching API or something like that internally this, but calling it here is a little bit more complicated. Or I don't know whether it's possible or not because it looks like a lambda function. So okay, we are about to look at an example showing how to work with Flink's key partition data. So we are looking at how the key partition state how the managed state which is partitioned by key works in Flink. So how do we use that? How do we use key partition state? How do we know that a particular state belongs to a particular key? Okay. Now, what it's doing is, okay, so we are looking at example, created this stream execution environment, we provided the event source, then we provided how do we key each of these um, events or message in the source. We process them by providing, we process them here, and this is a class which we have created, uh, I think this is most only a rich function. Yeah, I think it is a rich function which does the deduplication process for us regarding each event and regarding each event for a particular user, for each user, sorry, and then prints them. Again, then we execute it, we send it to our cluster. For the execution, okay, so let's look at the deduplicate. This is key process function. So this is a function which is executed for um, for each keyed event. So if you look at this one, so we created a key for each. So we provided a function which creates a key for each event. And what this will do is internally, I guess, it will mention that, you know what, this particular stream is key tagged. So there is a key which exists, which can be created for each of these events. So here we extended that particular reach function, which can be used for key partitioned events stream. So this is key process function, and we are extending it to deduplicate. There is this open function, as I mentioned previously, which is called once when we are initializing this particular function, when we have created a particular node which execute this particular operator, right? So what it does, it takes the config, it creates a value state descriptor, okay? So so whenever we are creating a particular state, it creates value state descriptor, which is, for example, when we do this at multiple nodes, this will actually this will actually be pointing to the same value state. Okay, so let's say we did this on one node one, it will see the scene variable which has Boolean type, and on another node it will also see the same scene variable. And if we update it on node one, it will be visible on node 2 as well, as right. So it doesn't have to like do get across the different nodes. It just knows that whenever this state is updated across the nodes, across the parallel execution, this particular state will be updated as well. So it just describes that particular value state. So this is a class, this is a wrapper which stores everything, and what we are doing here is we are storing that into value state, which is a wrapper, local wrapper, which stores the value and points to the state which is stored by the Flink cluster. So it's just a local reference to the state which is stored across the cluster. So, okay. So in order to set up Flink manage state, we need to use the rich function. As I said, this key process function is a rich function. Create a state descriptor that describes the data we want to store. So it says that, you know what, there is scene variable which is stored, which has a type Boolean. Bind a local state variable to the state provided. Local state variable to the state provided and handled by the stream. So we are binding this particular local variable key where key was seen to the state which was provided and handled by the Flink, as I mentioned. This Flink has some state. This is just a local reference of it. And open is called during the initialization before this function processes an event. This function processes any event. So this is called when the initialization happen for this particular rich function, rich class. So you provide it, and all information is wrapped in a special Flink data type. Value state in this case, this is a kind of a keyed state, meaning that Flink is prepared to store a Boolean variable for each distinct string. Okay. So each of the parallel instances of the will have the state for some of the keys. This is a kind of a sharded key value store. Okay, so I think we can explain this. So as I mentioned, each node will process each particular type of node and maintain the state for that particular keyed instance or keyed event, right? So this value state will be stored for each of those keys which is processed by a node. So each node will have certain value states corresponding to different keys that it owns. Another node will also have certain value state corresponding to each value state corresponding to the keys it owns. Okay, it's just not a simple single class which have every each class corresponds to a particular key, which we'll look at later how this particular how Flink scope this out internally. Okay. Okay, so let's look at this process event. So we have got an event, and it provides the context to us. It provides the collector output to us, what after we process. So this is a one-to-many. If you remember, we had that flat map. Flat map also had a collector which is used to provide one-to-many output for each key. So it says that key was seen dot value equals to null. If it sees that it has not ever been seen this key, that means the value for this variable for this key corresponding to this event is not seen ever. That's because it's null. Then what we can do is we can put it in the output mentioning this is the event which was the first event for this particular user or particular key, and we update this particular key that you know what, now we have seen this particular key, and we can use this state later when we try to check again whether the event another event comes for the same user, and at that time this null will not be null, this value will not be null, and we will not put it into the output, so we'll process it very fast. Okay, looking at the signature of the process event method, we see that receives context parameter. We are going to ignore this for now, but it is mostly used for implementing timers. So we haven't talked about timers yet because I don't know what that timer means. Now let's look at the business logic inside the process element method. In order to deduplicate the stream, we are checking to see if you already seen event for this key, meaning the key for the current event. To retrieve the state value, we call dot value. Okay, and to store a new value into the state, we call update. Now comes to the part that can be confusing when calling value and update. We haven't had to specify the key. Okay, before the framework calls process element method, it has automatically scoped state access to the key for the event that is being processed. So, okay, this is interesting. Okay, so to iterate, we have asked Flink to manage state for us, meaning it will be fault tolerant and survive crashes for the individual instances. Okay, so so what it is doing is, so if you remember, if you see in this case, it is not creating a key here, right? It's not doing something like event.key or anything like that, or it's not creating any key. So what is being done before this function is called is this function is called in the context of this particular event, and when this function is called, for example, this function is called value. when this function is called. So what it does internally is it takes, I guess it takes some global variable or somewhere, some scope which is provided, which is stored when we are processing this function, we're processing this process element function call. So there is some variable, some global variable, which this key was c dot value function looks at and sees that do we have a value for that particular key, and it automatically executes these functions for key, a valued function and update function for that particular key. I don't know um, whether it's implemented like this, but it's easier to understand like this, I think. So it's scoped for the particular key only. So it's not scoped for all the keys. It's scoped for that particular key corresponding to that particular event that we are processing right now. Okay, so there are different types of key state. There is value state, there is list state, there is map state. We can store values only just like a key value store. We can store list as well as corresponding to for each keys. We can store map corresponding to each key. In this example, we use the simplest and most general purpose of the types of key state that Flink provides, but there are other than the others. Rather than value state, use list state. It's better optimized. Okay. I think for this storage, right? I think these guys use like RocksDB internally, I guess. So map is also scoped because it has some optimal storage for these key value pairs. Map state also scoped by key. This is a nested map useful, for example, if you want to store an open-ended properties. Useful, you want to store an open-ended properties hash for each key. And if you want to store an open-ended properties hash for each key in a key stream, another common pattern processing. Okay, and the common pattern processing out of order event time data is to use map state to store data for different points in time. In the scenario, map state entries they keep processing time paired with the data relevant to that point in time. There is an example of this in the slides about implementing windowing with process function. Okay, so that's what I mentioned, right? So with RocksDB, map state is much more efficient than value state of hash map, and reducing state and aggregation state are also available and can be more expressive in certain situations. So let's look at those. When is state garbage collected? By default, Flink returns the state it manages forever. Okay. Timer can be used with key process function to clean state. So we can have certain timer function here, I guess, which cleans up the existing state after certain time. Or what we can have is a state.ttl config, which clears the each state automatically after certain time. So we provide this during the state descriptor. So we provided this state descriptor here, right? What we can mention is the TTL here as well. I guess I'm just guessing. I haven't looked at the code here as well, and that can automatically dispose of the state after a certain time. Okay, so can be cleared based on the time since last write or last write or read. Yeah, okay, so this state detail was added in here. State retention interval in event time has been described but is in under active development. So this is not actively developed. I don't know why this will be used. why this will not. I guess this is what the standard way of doing it because it's more open. We can actually what like if there is a timer function, what we can actually look at different things, dif not just the value or last time. We can look at many different things and then decide whether we want to clear the state or not. Let's say, for example, a user session is switched off, right? Then we can go ahead and clear the state for that particular user. And for that, we need to check that uh, whether the session exists for that or not. So which we cannot do here because it automatically does everything here. So it's like a superset of functionality this function can provide as compared to state retailer. I guess that's why it's not um, in active development. Okay, okay. So now let's talk about connected streams. Okay, so connected streams. So to connect two streams, to process them together, connected stream can share state. The two streams must be key and compatible with. Oh yeah, okay. So as I explained before, right? So there are two streams which are coming together, keyed by the same key space and processed by the same node. Okay, we can connect these two streams and maintain a same state for these two streams. Keyed in a compatible ways. Okay, the keystone can be shared stream. That's what I said. Connect two streams to process them together. Connect two streams to process them together. Yeah, give me a second. Okay, okay, okay. Let's look at this very frequently use case you would like to, it is very frequent use case you would like to connect two streams together and process the event of both, influencing each other. Okay. Hmm. Okay. Such connected streams can share state because the state that they share is key. Both stream have to have keyed using the same key space. It wouldn't make sense to key one stream by user ID on stream, of course, right? Otherwise, these will have different state, not the same state which are connected. So let's look at the example of this. So we have created this stream execution environment. We have provided one stream which is keyed by the string which is provided drop ignore, right? Another stream which is Flink drop forward ignore. Same thing, keep but the same case. So what this do is there's a control stream, we are connecting data stream with it, and there is this control function, the rich function that we have provided to process each of these events and then print. So we need to look at what control function does. Okay, so we are looking at control function. Okay, so there is this open function which we already said. There is a variable which we are creating blocked, which is a Boolean class. Okay, and for whenever we are processing element one, which is I guess control, we are updating whether this particular key is blocked or not. event is blocked or not, right? So we will block, drop, ignore will be marked as true, and when we are processing element 2, which is data, Flink, drop, forward, ignore. What this will do is it will look at the blocked value for that particular key, and if that value is null, then it will say collect that particular data value. So in this case, it's just blacklisting these drop and ignore from this list, and we can just this will just return Flink forward. Analog this to key process function that operates on two different memory. We need to implement not just one but two process implement functions as when with the arrival of events of the connector string when we receive event of the control when we receive events of the control string which are words we should block. We just show a rebellion flag. Both strings are keyed by the same key, the actual key, the word. And this guarantees that this word arrives on the system will accept the same flag, only pass through words that haven't been blocked. The two streams can race against each other. Okay, so you have no control over the timing when the element of those streams get processed. Okay, later we talk about mechanisms in order to get some determination of the receiving part. So okay, so another thing which might happen is which so concurrency issues, right? For example, each of these keys events are processed first, right? Then what happens is this block value for each of those keys will always be null because none of the stream uh, first stream has been processed. So all of these values are null. So it will process first and then the blacklist will be assigned. So there are certain ways to deterministically process these streams. But I don't know what those are. So I haven't looked at it, but yeah, there must be a certain way, otherwise it's useless, right? Because if we cannot say deterministically how we are going to process these two streams, in this case particularly, then it's pretty useless. Okay, so how does connect compare to union? Okay, so give me a second. Yeah, yes, how does compare to union? So there is connect we use here, right? So there is this connect we use, which kind of processes connects this to a string. What does union does? Union merges n states of the same type, n streams of the same type. So these are two different streams of the same type and it merges them. Connect works with two streams of different type. You can tell from which input channel element was sourced. Okay, so in this case, we know that there are two streams which are coming and each event knows where it is coming from. But in union case, all of them have we don't first of all we don't know how many streams that we are merging. It could be more than two, it could be more than three, and um, from which stream the particular event is being processed. So I guess this is what happens when merging we are merging similar streams, similar type of streams, and we don't care about we don't care about distincting each event, whether it's coming from one stream or another stream. For example, in connect case, we had to know that this is a stream which contains a blacklist, and this is the stream which contains the regular events which are coming. So in this case, I don't think we can know which stream is being processed, which function is processing which stream. Oh, sorry. Um, which event is coming from which stream. It's just one single stream out of n different streams. Okay, so let's look at the summaries of links. Managed key state is sharded key value store. State is always local to the operator instance. Using a state is held in state backend, which can be on the JVM heap or on the disk, of course. So using it, heap and disk link takes care of checkpointing, recovery, and rescaling. Okay. As we already saw in the design earlier, in the last part one, I think, where it mentions there is module present there which does checkpointing, recovery, and rescaling. Operators with tooling can have state that is shared between the two callbacks handling the incoming events. Okay. Isn't the only kind of state Flink. Okay, so keyed state are not the only kind of state the Flink can manage. There are something called non-key state, which is sometimes called the operator state. Non-keyed state is seldom used in user code. For the most part, is only used in implementation of sources in sync. Broadcast state is one of the kind of non-keyed state that is somewhat commonly used outside of framework itself. So there is another kind of state which exists. So we were using keyed state, right? There is another kind of state which is like broadcast state. I don't know how it is implemented and how it is used, but it must be for the scenario where we are broadcasting the data stream across all the nodes in the next stage in the DAG. So each event is sent to all the nodes. So it's like broadcasting each event, and there must be somehow a use case for using that. I'm guessing. Yeah. Give me a second. Okay. That is there. And best practices, of course, avoid using value state with collection classes. As mentioned, there is optimization done by RocksDB, uh, which you can utilize with list state and map state instead of doing value state of list or value state of map. Don't register to do this, but don't register state in open instead. Huh. So get runtime context, get context. Okay, so registering state descriptor in open and unifies the semantic across both state backend. In particular, this will ensure that any state migration is done during the startup phase rather than lazily, which might stall or crash it. Okay, so I guess doing it lazily, the state initializations lazily might cause problem because it expects you to initialize every state in open, and when the open function is done, is returned, each state should be initialized. But in lazy case, it might not be, because lazy state might think that when it is used later on, and then it can initialize at that point. But what it can do is it can stall or it can cause issues with the job execution because it needs those state there when it is calling those process element function, I guess. And if it doesn't see that, because I guess it can cause problem. Yeah. Okay, traditional tiered architecture workers local state. So traditional scalability. DB may bottleneck needs scaling in addition to app compute and storage co-located scale side by side. Okay, so this is something different, right? I don't know whether this is a good argument or not, but in this case, for stateless applications and database being different and needs to be scaled, we can scale just the database or just a stateless application or both. So that is more flexible as compared to the streaming application which have state which is tied to the state and scales in a proportional way. So I don't know how that's useful because it might happen that we need to scale just a stream application, note the state. Let's say state is not fully used, or then we are unnecessarily like the state is not fully utilized. Then also we are scaling. So we will waste some storage, I guess, in that scenario, which is, I guess, not ideal. But I guess you can do it easily. You don't have so many moving points. I don't know. I don't think this is something positive. Does it mention it's positive? So as we wrap it up this section, it's was in how Flink's approach to managing scale state compares to how state is managed and scaled in more traditional system. Okay, so it's just comparing it. Okay, that's fine. So I guess this is more better approach as compared to this. But anyways, maybe there are certain configuration that we can scale these two stuff individually. So performance, right? So read and write across tier boundaries. Okay. Local state plus asynchronous write to a large block for durability. What do you mean? Read write across tier boundaries. Okay, so like tier 1, tier 2, tier 3 storage like archive and persistent storage, something like that, hot storage, cold storage, something like that. And this has okay. Operational simplicity, deploying a new service and managing other database. How? It's not bounded, right? Like two different applications can use the same database. Only additional only additional backup storage needed, so that is fine. The only backup storage talking about is the checkpointing stuff, right? So you checkpoint, you back that storage up so that when it needs to be recovered for, let's say, when you're creating a new instance of the node or restarting a particular node, then this backup storage will be needed. Consistency. Distributed transaction, usually low isolation and consistency. How? Distributed transactions, usually low isolation and consistency. I mean, you are taking the worst of that and best of this. How do you compare that? There is different transaction, high isolation. Okay, fine. Um, exactly once per key with. I guess this is talking about an architecture which is used for current streaming applications. So this is a streaming application if Flink is not used, which stores data in database, I guess. Provides low isolation. Maybe it's using some database which provides low isolation and consistency. I guess and in this case it is just exactly once per key with Apache. So each state is updated only once per key. So okay, each event is processed only once and each state is manipulated only once per event. I mean the operation transaction that you are doing that happens only once. Okay, we are done with this. Okay, let's look at fault tolerant. So with fault tolerance, yes, state snapshot. Okay, exactly one guarantees. Okay, enabling and configuring checkpointing. Checkpointing was the save points because I don't know what that means. Is it like checkpoint? Is checkpointing like you want to reduce the data that we are storing, right? So it could be just like a linked list of diffs across different states, right? Something like like each of these state which we are checkpointing has LSNs and we are just storing the diffs across the state. Okay, anyways, we will not speculate here. So fault tolerance via state snapshot. Okay, give me a second. Give me a second. Okay. Okay. So okay, so let's look at this fault tolerant via state and how do we take state snapshot. So this is a stream. These are different nodes which have certain codes in the tag. It has some state stored. And what we do is we have this central storage where we are storing each state when we are doing snapshot. Checkpoint state, checkpoint state, checkpoint state file system we are storing it. The snapshot records the offset. So how do we do the snapshot? Snapshot records. Okay, so we cannot, like for example, if we just copy, we need to freeze the state and then copy it, because there are still that state is still being manipulated by our code, right? So we cannot do that during runtime. So we need to snapshot records offsets in the input queue and the state throughout the job graph. So the offset in the input queue and the state, and I think we can do that. In this case, we can do that. We can create we can store it separate file. We can take it the snapshot locally and manipulate. So if you are okay, so how it happens is for each of these state, we can have create a new file. We can start manipulating that file, and in the meantime, we can just back up this file which has already been freezed. That's one way of doing it. So what it does is how a state, a particular snapshot is defined is an offset of the input queue. Okay, the front of the input queues. So the offsets in the input queues. So offset of what message we are still, I guess, have to process or is processing, and the state throughout the job graph that resulted from processing the data to that point. So we processed all the messages in front of this queue event, and we have certain state present, and each of that state is stored here along with the offset. So this is defined as snapshot or checkpointing, I guess. So at runtime, if enabled, Flink takes consistent, distributed, and asynchronous snapshot of your job's state. These snapshots rely on checkpoint barriers. Barriers for snapshot N are inserted at all sources and traveled through the job graph with your events. Okay, so I don't understand what that means. Okay, so when an operator receives barrier N on all of its inputs, it takes a local snapshot and stores it in a remote durable storage. The checkpoint is complete when all tasks have finished their copies. Okay, so this I understand. Checkpoint is complete when all tasks finish their copies, which is this. When an operator receives barrier N on all of its inputs. Okay, so what is a barrier first of all? Barriers for snapshot N are inserted at all sources and travel through the graph with your event. Okay, got it. So I guess what happens is, in a stream of events that we are processing, it inserts a barrier or it inserts certain messages which act as a barrier. And what happens is when every of these nodes, your in this example, this your code, it when it processes that barrier, it snapshots the state and stores it into this file system, and this particular so there must be some barrier ID which is given, and this snapshot corresponds to that particular barrier ID. So what happens is, okay, so this is very cool, okay. Because see, these events are queued in a certain order, right? And that barrier is also inserted in a particular offset. So everything which is in front of that barrier is already processed in each of these nodes, in this. So the state we get when each of these nodes are processing that particular barrier is after processing everything which was in front of it. So when we take a snapshot of each of these states, and when it is processing that barrier, it is consistent across, because all of these nodes have processed all of these events in front of it, which are in front of it, which are in front of the barrier, of course. So this is nice. This is nice. Okay, these snapshot so rely on this, and this only happens when you have everything in queue. You have certain order, you have a particular total order on all the events, which is provided here by the queues that we are streaming on. So these snapshot rely on, so let's read it again. These snapshot rely on checkpoint barrier. Okay, barriers for snapshot N are inserted at all sources. Travel through a job graph with your event when an operator receives a barrier N on all of its inputs. All of its inputs. Okay, so it needs to receive barrier N in all of its input, right? Because it's processing multiple inputs at the same time. It takes a local snapshot and stores it in, okay. Okay, so actually that happens across multiple queues, just not this queue, right? So there are, okay, so how do I explain it? Okay, so let me see if I can explain it. Let's see. Can you guys see my screen? I know how it works, man. This is okay. At certain point, this becomes useless. Okay, so how this works is, so There are a lot of streams which are coming here, right? So the lot of events, lot of different events which are being processed, and there are certain operators OP1, there are certain operators OP2, certain okay, sorry, certain state which is stored here, certain state which is stored here, and let's say goes to a same operator. You will say graph, right? So that graph. So state stored here, and we have central storage, persistent storage here. Let's see. Okay. Now we look at what the snapshot means. Okay. So what we do is when we are putting these events, when we are putting these events into the stream, right? We are going to do is, depending on the configuration, we are going to put a particular barrier at certain offset for each of these strings, right? So this is, let's say, offset 1020, let's say, right? So this is also this is also inserted at offset 120, no, 1020 offset, and this is also inserted at offset 1020. Okay, so when these particulars are processed which are in front of these offsets, what will happen is, in a snapshot we are going to store this offset. Okay, we are going to take a snapshot of the state, and remember that. So this thing is now processing this particular event, which is called a barrier. Okay, so processing barrier right now, all of that, right? So what they do is, it takes a snapshot of the state when all of it, so it is processing all of these queues right here, and when all of them receives a barrier, what it does is it takes a snapshot of it and puts it here. Same for this case. We store this state OP2, something like that, right? So what it says is, you know what, at this particular offset I stored the state of all of these operators and stored it here. So you can say this represents a consistent state at that particular barrier of all of these operators, right? So this only happens if we have these kind of queues, right? If the queue doesn't exist, then this event might go early, right? Or this event might go early. This event might go early, right? There are no orders, so we don't know whether all of these events which are behind it are processed or not. So that will not create a consistent state. Only consistent state, the reason the consistent state is being created here is when we are using queues, and we are putting barriers here, we're indicating snapshot, and this because this provides queue provides a total ordering. Um, this is the reason why this is um, consistent. Okay, so yeah, that's the reason why this is consistent. Okay, now let's look at each job life cycle and fault tolerance. So we have already looked at how the snapshot happens. So this is one part of the story, right? We are executing each task. These are all the task managers. Now we need to talk about how do we use these states to overcome a fault or a failure at runtime. So on failure, when the task manager fails, it cancels the job. When the task manager fails, when the task manager fails, it cancels the job on all task manager. It cancels that particular. Does it cancel all job, or does it cancel just that job? Because if let's say it does only cancel a single job which fails, if let's say if it just cancels the job for which the task failed, then other jobs will keep on continuing and the state will change for those jobs. But does it matter? Because state is corresponds to each job, right? So the task manager fails. Okay. Fails. The task manager fails. Like this restart will follow your selected restart strategy. If the job manager fails, the TM, the task managers, will cancel the job with job manager high availability configured. A standby new job manager can take over and restart the job from the last known checkpoint. Okay, so we are using replicas of job manager here to provide high availability, and whenever the failure happens for job manager, that particular instance is gone and is replaced by the replica that we maintain parallelly for job manager, and that particular replica will start processing events from the last snapshot, right? Because, and okay, so in that case, for example, it might happen that after the last checkpointing happened, certain events were processed and states were changed, and then the failure happened, but before the next checkpoint, right? But before the next point, the failure happened. So certain events were processed, and those events will be processed again by the new job manager replica. And if okay, so what happens is if the job manager fails, then it's anyways going to start from a particular checkpoint which has already been done, right? So there is no need to run any existing task which is running. So it cancels the task managers, it cancels all the jobs which are running, and okay. So this is a little bit fluctuation, right? So I don't know how much lesser latency issues it will cause, because if the task manager fails, so let's so this is fine, we can take a look at that later. But if the task manager fails, then there will be a strategy that we will use, I guess, which is mentioned as restart strategies. So let's look at the slides first. So task manager fails, cancels job on all task managers. A restart may require new task manager slots. Okay, so cancel job on all task managers. Okay. Cancel job on all task managers. And if a particular job is being executed, this is streaming that output to another job, another task which is being executed in parallel. So this task is failed, then then the next stage, the task in the next stage and in the previous stage will get flagged because it's not able to stream across the node which has failed. So all other nodes which is processing that particular task is also cancelled, and the task and the job is restarted. But how do we, let's say the checkpointing happened, right? And how do we make sure that we pick up the state when the job actually started, right? So for example, we started the job J1, we processed certain tasks of it, we manipulated certain state. Okay, we manipulated the states at each operators, and after certain time a particular task manager failed, but the state is changed, and let's say checkpointing also happened. Okay, so checkpointing happened and stored the checkpoint. What it can do is it can start from the last checkpoint only. So the restart here, will happen. So the restart here will happen from the last checkpoint only. From the last checkpoint only. So then I don't know what the restart strategies are. Let's look at what the restart strategies are. Fixed delay restart. Failure rate restarts, no start strategy, fallback restart strategy. So restart strategy, fixed delay. The fixed delay start and a given number of times. To restart the job. If the maximum number of attempts is exceeded, the job eventually fails. In between, two consecutive restarts and waits a fixed amount of time. That's fine. Okay, but how does the restart happen? I guess restart happens for that job. Restart happens for that job from the last checkpoint, if I have to say. Okay, so the failover strategy, that's what we are looking at, right? So this is the failover strategy that we are looking at. This is what we want, like restart, like different strategies can happen for different restarts. I mean, there is no restart required here. There is a failure rate, like how many times the restart has happened. There is, in this case, there is a particular delay which is added in between multiple restarts. So all of these are different strategies to do restart. But how does the restart actually happens? So these are the failure over strategies. Support different failure strategies which can be configured via the configuration parameter. Configuration file can config. It's all over. Clearly restarts all the tasks in the job. Okay, this strategy restarts all the tasks in the job. Okay, so what it do is for a job, it restarts all the tasks again to recover from a task failure, but this will cause a problem, right? Because let's say when the failure happened, the state was changed. So when we reprocess those tasks in a job, it will execute on top of that state, which is wrong, right? So this strategy is another strategy here is group task into a disjoint regions. When task failure is detected, this strategy computes the smallest set of regions that must be restarted. Smallest set of regions that must be restarted to recover from the failure. So let's say for example this particular task restarted or failed. Then all the nodes, all the tasks which are affected by the failure of this task node, you create this joint region for that failed task, smallest region of course, that needs to be restarted, needs to reprocess all the jobs from the last checkpoint. A region is a set of tasks. Okay, so for some jobs this can result in fewer tasks that will restart compared to restart or failover strategies. Of course, a region is a set of tasks that communicate via pipeline data exchanges. That is Batch data exchanges denotes a boundary of the region. All data exchanges in the stream batch by default. No determination mode, which can be. Um, okay, so the region containing the failed task will be restarted if a region, if there is. Okay, pipelined in action. So okay, so we don't. Okay, so region in this. Okay, so another. Like on the other hand, what region here means. So, so there is a set of machines which are locally present, I guess, which transfer the data across them for a particular task. Like we don't have to transfer the data across different regions just to process the one particular event. Okay, that's good. Or one particular event in a job graph. So yeah, okay. The region containing the failed task will be restarted if a if a regional partition is not available while it is required by a region. The region producing the result partition will be producing the result partition. If the result partition is not available while it is required by a region, that will be started. The region producing the result partition will be restarted as well. If a region needs to be restarted, all of its consumer region will also be restarted. This is to guarantee data consistency because non-deterministic processing or partitioning result in different partitions. Okay, so what it's trying to say is that there are different regions and each region have certain jobs inside them which are running. And let's say these two regions are connected because the output of this particular region of this particular job which is being processed by this region is passed to this region. Okay, and the failure happened in this region. So first of all, this the task in this all the tasks in this region will be restarted. All the tasks which were connected to this region which failed, which is this region, will be started and further on, so that we maintain a data consistency because of non-deterministic processing or partitioning which is happening. Because if we look at this further, then we have more clarity on how this is happening internally. But all of its consumer region will be started. Because it to be restarted. Let's say this region is restarting, right? All of its consumer regions which are consuming the output of this output of the field region will also be restarted. This is to guarantee data consistency because non-deterministic processing of partitioning. Because let's say the partitioning happened, can result in different partitioning. So it might happen that, okay, so I guess that's what it means. I'm not sure. So let's say this is the region in which the node failed. Okay, what happens is this whole region will be restarted, and let's say there is another region here which was consuming from this region, the output from this region. So, and the output from this region was partitioned in a non-deterministic way. So let's say when it failure happened, it partitioned certain way, and when we do the restart, it partition different way. And what that can do is it can cause problem for this because it will not be able to use the old partition way which it started the job with. So this also needs to be restarted. It all happens because of non-deterministic processing. So if you are doing non-deterministic processing, if you are doing if you are doing non-deterministic processing which is not consistent with what the processing was before the failure happened, then that will cause problem. So that's why it tries to find all the regions which will have problem. If we restart this particular region, then it will fail all of those regions and restart those. So it's just trying to find a subset of region which will restart during a failover. And this is another strategy which just blindly restarts every region. Okay. So this way already explained cancel job for all tasks. So if the task manager happens to be cancelled, then we do this failover where we restart all the tasks, where we restart that we cancel that particular job. Okay, and we restart the task manager which was failed, and we restart all the jobs whose tasks were failed when the task manager went down. So it will try to make sure that that restarted task manager will return to the stage before the failure happened. How do we do that? Right, so it cancelled all the tasks who were passing through this particular task manager. Okay, and restarted all those. It will cancel all the jobs, sorry, not the task. It will cancel all the jobs whose tasks were passing through this particular task manager which failed, and restarted all those jobs from the last checkpointing stage, provided last from. So what it will do is it will, from last checkpointing stage, it will provide the state to this particular task manager, and then execute all the jobs which we executed, all the jobs which you cancelled after that checkpoint, all the tasks which we executed for all the jobs after that checkpoint. What this will do is it will rebuild all the state on all the task manager which are still running and the new task manager. Okay, so that's what I understand right now. I'm not sure because we just started this. Operator code fails, cancel job on all task manager. Operator code fails. Cancel job on RTM, restart. Okay, so let's look at how the recovery happens. So restart all of the workers. Okay, recover all the state, including positions in input stream. Important consequences of snapshot data or snapshot are globally self-consistent images of state throughout the cluster. This means that in general it's not possible to just restart the one worker that failed. Of course, only one. All of the tasks throughout the cluster have to have their state reset from the state in the snapshot, and everyone is rolling back to the same earlier point in the input streams together in a coordinated way, of course, because it is the one system, right? So what does exactly once mean? So what happens if a worker goes down? What happens if a worker goes down? How is Flink stat affected? Flink supports different level of guarantees for failure recovery. Exactly once checkpointing has somewhat more impact on the ongoing stream processing. This may show up as a back pressure or increased latency compared to at least once. So it needs to make sure that every event, I guess, is processed exactly once. And as we need to do that, it results in certain trade-offs in terms of back pressure in the queue, in the stream, and increased latency because of that, as compared to at least once. Okay, let's see what exactly once means. So if checkpointing is deactivated, all state is lost if there is a failure. So if we deactivate checkpoints, right? So the same events might be executed multiple times. Might be executed multiple times, or not exactly. So what happens is, let's say we don't have any checkpoints. Can we maintaining a state and that particular state is gone after a failure? What happens is we don't have checkpoint. We'll start the task managers. We'll continue executing from that same point, like from we'll start continuing this string. We will not revert back or do any recovery. We'll start continuing. So that means all all the state which was changed because of previous events is nullified. Okay, so that gives us the guarantee of at most once when we are not maintaining any checkpoints. At least once. Each event affect the at least once. Okay, so at least once is a little bit complicated. At least once each event affecting at least once, the replayable sources will be rewound and replayed, but it could be that the records are considered twice in the calculation. If all of your operations are idempotent, this could also produce completely correct result, or you may be willing to tolerate some duplication recovering from failure. So what happens in this case is, instead of checkpointing the storage, what we do is, when the failure happens, the state is at least once each event affects the at least one, the replayable source will be rewarded. Okay, so when the failure happens, for a particular event, that particular event is replayed. Okay, and when the replay happens for that particular event might be executed by an operator multiple times, and if that happens, the state has been manipulated multiple times by the same event, which will cause result to contain some duplicates. But if your messages or events has idempotency in them, then you can take care of it in process element, I guess. Okay. And this failure happened, and this node went away. Task manager went away, and we created a new task manager. We provided new task manager and replayed all the tasks from the last checkpoint. So all the tasks last checkpoint might get. So something like this. Give me a second. Okay. So what can happen is so first of all, let's look at deactivated checkpoint. So in deactivated checkpoint, when the failure of when this node, let's say, okay, when okay, I think it's not visible. So when this node fails, what we do is we just restart another node which acts as a new task manager, and so let's sorry, give me a second. Okay. So let's say this was a task manager and it failed. It contained a lot of operators it was executing, right? And this failed, let's say, right? It's not there anymore. What it does is it creates new task manager. We are talking about the first case, which is at least not at least, at most once. So in this case, we'll restart this, we'll create this OP1 operator, but the state we had previously will not be present here. The state here will restart. Okay. So, and what we do is when the failure happens, we will start executing from that point onwards. For example, there was this queue which we were executing and the failure happened here. So what we'll do is we will again process this event next without restoring the state here. This event here, but without restoring the state here, which will cause problem with this state, because this state doesn't have events like this, which are not processed for this particular state, which is restarted, right? So that's for at most once when no checkpointing exists. But if the checkpointing do exist, what we can do is we can provide a guarantee called at least once, and by this I mean is a message can be processed multiple times by a particular operator, right? So let's take this example. So this is the task manager. Previously it has OP1, OP2, it failed, it had some state also. It created a new task manager, OP1, OP2, and and what we did was we restored this particular state from last checkpoint state, okay, and this last offset also that we last offset in the streaming queue that we shifted to, right? So we shifted to this again. We will process all of these message again and this will change the state here, but what it might happen is all the other operators which are connected to this will not be restored to this state because it's not a full failure. It's not a full failover which we are doing. We are just doing failover for this task manager, reverting the offset to the old one and deprocess again. So what happens for this operator here is it already has effects for these events. These operator already has the effect for those, but when we process these events again, these operators will process those events again and manipulate those events again in the state, which will cause some duplication in the state, and I guess it will make the state inconsistent or correct, but you can handle it other way using add potency with your events. So that's one of the things that you can do. Right, so another stuff. I guess exactly once we already talked about, I guess, but let's see what it says. Exactly once, so each event affects the managed state exactly once. Does not mean that events are processed exactly once. More performance impact than at least one, of course, right? So we already talked about this. So we talked about the failover, right? So all the task managers. So let's say this is task manager which was failed, right? So there are certain operators in this OP1, OP2, and this OP2 was connected to another task manager, another OP here or here, right? So all of these will be restarted and state will be taken from the last checkpoint. State will be taken from the last checkpoint for all of these, and and the offset in the queue will also be reversed, and all of these events will be processed again. All of these events will be processed again, and it will create a state here which is consistent with processing each of these events only once, right? That doesn't mean that these events were processed only once. For example, in this case, before restart, a particular event was processed and the same event was processed after restart. What it means is the state that you are getting here is for exactly once. No, that was my part. But of course, you can see there is more impact here, right? Um, okay. So Failover involves rewinding and replaying the sources. So we are only reprocessing and what we are able to guarantee is that the state being managed by Inspector exactly once. That's what I said, right? Or at least once if you chose the weaker guarantee. So it depends on what kind of guarantees that you are using, what kind of recovery configuration that you have mentioned. Okay, so exactly once end-to-end, exactly once and at least one guarantee requires repeatable source that I mentioned. Ververica will be replayed in case of failure. To achieve exactly once end-to-end, you must have a transactional sync, okay, or be satisfied with idempotent writes. Exactly once results are correct, but may be produced more than once. Exactly once end-to-end. Results are correct and produced only one to one. So there is a difference between exactly once and exactly one end-to-end. Okay, so exactly once means a state across the operators will show that each event was processed only once. That's it, and the sync can get the output for the same event multiple times. But in exactly once end-to-end, the sync will only get the output for an event only once. And results are also correct, of course. So far we have talked about how by that we are just looking at how values stored in links are affected by the event stream. In other words, ensuring that streaming is only affected once can still lead to sinks being spent duplicated. Of course, if you cannot accept duplicates in the output, think about processing money transfer. You need to have exactly once guarantees end to end. Okay, so fault tolerance guarantees, no checkpointing, exactly once, end to end. So all of these will have replayable except the no checkpointing one. The sync needs to be transactional, quite important when we are talking about exactly once end to end, because there may be multiple, there is no the sync needs to be transactional because it needs to make sure that it needs to handle the cases where we might output multiple times for the same events. So okay, so this is produced one, this is reproduced after the recovery, and no checkpoint correct result, so there is no incorrect result. It's over, so I wanted more than once. So yeah, I understand. Yeah. Guarantees of some of the data sources. So this exactly once in Kafka, Kinesis, RabbitMQ, collections, files, sockets. It doesn't have any. It's networks. File sync, Kafka, all of guarantees here. Exactly once also Ververica, Cassandra. Exactly once for important updates. Idempotent indexing, at least once for Kinesis stream for data. Okay, so this is data sources. So exactly ones are provided, exactly ones are outputted. So this provides exactly ones for idempotent updates. So as we saw earlier that there is idempotent update or transactional update which is needed at the sync side. So there are syncs which have exactly ones with idempotent update or idempotent indexing. So there are certain syncs which are at least ones. For the second is not a server for the budget thing that is Flink. Okay, that's fine. You can always guarantee correct result in batch mode by restarting from the scratch if anything fails. Exploring finding recoveries of founded data sets on Flink for more details, that's fine. What about better straight and snapshot for checkpointing are only used the streaming job because intermediate states are not present, or we need to create those states using those recovery procedures that we mentioned. Execute proceeds in stages. Completed stage materializes to disk. If the stage is failed, it is restarted. In the worst case, the job can be restarted from the beginning. So this is very similar to what Hadoop has. So this is very similar to that. Usings that implements try to guarantee exactly once in batch mode. But there are cases where records are lost if a task manager fails while the sync is writing. I don't know, so we'll look at that later on. Legacy sync provides no guarantee in batch mode. So there does exist exactly one in a batch mode. Huh. Because we are maintaining a state, right? If the failure happens in the task manager, it restarts all the time from the last state which you were storing, right? It restarts that and look at that. So what it says is for batch, so we were doing checkpointing in streaming, right? That is already done in a very simple way for batch processing because batch processing output at each stage is stored in the file system. That's what the checkpointing is. And I guess rest of the exactly one's part is similar, but it says there are some edge cases where records are lost if a task manager fails while the sync is writing. So I guess we'll see about that. Um, okay. So legacy sync provides no guarantee. Enabling and configuring checkpoints can be done either in Flink configuration or in your code. There are settings, but the most important are where checkpoints are stored, how frequently they are triggered. So checkpoint needs to be stored in a persistent storage, and how frequently they need to be triggered. We need to put that. What was that? I forgot. So you need to put that barrier in the queue in the stream, right? So how frequently we need to put that? We need to configure that. Checkpoint storage is a job manager checkpoint storage. Checkpoints are stored in the job manager C. This is the default, no configuration required. Okay, okay, file system job. Okay, so different checkpoint storage, right? So it all of the checkpoints are stored in the heap of the job manager, which is so weird because the state could be very high, uh, but depends on the usage, I guess. File system checkpoint storage. Checkpoints are stored in distributed file system, recommended for high availability deployments, require specifying a URL file either in Flink configuration or in your code. So it mentions here where you need to store that, you need to put that there. Okay, so you have two options for but this is only very rarely a suitable choice for production. You will almost certainly when want to store user code in this total file system prior to being exactly about different and another version of the front that was provided to the state backed. Backend constructor, okay. I don't know how that matters, but okay. Checkpointing is enabled by setting an interval, so 10 seconds. Here, the factors to consider when considering how long it may take the cluster to catch up during the recovery. Try to make sure that we don't do a big interval because it will take more time to recover as well as backup. But lower, if you go very low, the checkpointing will happen more frequently, will require more resources, it's happening more frequently. Of any transaction experience the consumers of any transactional sync. Okay, so there are runtime overhead involved. So suppose you have a job that is intended to be operating in a real time. You have set your checkpointing interval to something rather long, like 20 minutes. If the job failed and has to recover, it will probably take quite some time for it to catch up to where it is once again operating in a real time. And it will have to be processed all data received since the last checkpoint has transaction. That's what I mentioned, right? So if it is a near real time, you need to make sure that the interval is small. You need to not provide like 20 minutes. So transactional syncs, and if you provide the less, like the time, the interval is less, then it will require more resources, which is obvious. Okay, so transactional things such as Kafka and file sync only commits transaction as a part of checkpointing. So downstream consumer of your job's output will experience delay governed by the checkpointing interval of your job. So transactional syncs such as Kafka and file sync only commit transactions as a part of checkpointing. So okay, so and I understand. So what transactional sync means is whenever keep on producing output the similar way we do for normal sync, but during the checkpoint we do the checkpoint of each state. We do the storage of each state from each operator task manager. We store that offset of the queue. We also do the commit transaction on the sync side. so that whatever output we have produced till now are committed. So if you do, so if you do have intervals quite high, the transaction will happen less frequently, right? In those cases, or let's say if you do put the interval checkpointing interval as very less, then those transactions needs to be processed at that frequency only. So yeah. Yes. Snapshot is the generic term. Checkpoints and checkpoints are kind of snapshots. Broadly speaking, checkpoints are manufacturing intended for Ververica. These checkpoints are user triggered, searched, and definitely intended for manual operation. That's fine. Okay. So looking at this, this is a Zoom link. How is that a Zoom link? Wow. Okay. Okay. Huh, of course. So we were here. Yeah, so these are all tags which will see these tags there later on. That's fine, I don't. I will not pay you guys. That's fine. Okay. So state backend. Okay, Flink relies on state backend to manage and checkpoint storage for timers and key state. Okay. Based on JVM, so there was one way of storing it into the memory, which was JVM heap object, which is there in the left here. And if you want to store it in a persistent storage, it has to go into the rocksd. The state backend are only used for managing key state, non-key state, which is most often used in source and sinks. Purpose case is always on the heap. Flink has two state backends, one based on objects on heap, another based on RocksDB as an open source ended key value storage library, embedded key storage library that persisted to the local disk. Flink does not expect the state in the state backend to be durable in the event of a failure. Any state on the heap or again may be lost. Instead, checkpointing copies the state from the state backend to the distributed file system. So based on support for incremental checkpoint, hash map, state backend, objects in the object heap. So if you are using RocksDB, that the checkpoints can be incremental. Both state backend participate in checkpointing, of course, with RocksDB incremental is highly encouraged but not the default. Watch for progressing incremental snapshot for heap-based state backend. Looking for progress on generalized incremental checkpoints. Okay. Heap has higher throughput, lower latency affected by GC overhead and poses. So GC in JVM can delete a particular row. The key value storage or an object in the key value storage depending on whether this object is referenced or not. So there is GC which runs every after each interval, which blocks the update in memory objects, which can cause delays. High memory overhead for representation, so it will cause issues. You'll need high memory, of course, but if the state is less and you want frequency, you can just use in memory itself. But if you have less memory than the state you want to store, then you have to use files, which will give us high latency and less throughput. But yeah, assignment by available local disk, order of magnitude is slower, serialized overhead, serialization overhead, discussed of course. So legacy state backend, memory state backend, hash map state backend, plus job manager checkpoint storage. Okay. New backend state backend plus checkpoint storage. Okay. So we are creating a hash map state backend plus the checkpoint where we need to do the checkpointing, whether in file or in memory. There's another thing which is RocksDB. You want to store it the state locally on each node in RocksDB and store it in file system when we are checkpointing. Okay. I guess that's it for now. We'll look at this time developer training next time, and I guess we need to do all of these and then do certain coding, write certain example. I'll set up my my Flink, Apache Flink before that, so that we can do certain. I'll also figure out certain examples which will explain the transformation, the different operators, failure cases, recovery cases, I guess, if possible. But I don't know if it's possible because we will not be able to do a long standing and how the failure will works. I don't know. So we'll have some basic example, at least good enough basic examples. for each of these states, so how the states are manipulated, different APIs that Flink provides, the table APIs and all the state APIs. And what we'll do is, then there is this time window processing, which is what the next bash training will be. So we can look at that next time. Okay. Thanks you guys. Bye.